Welcome to the third lecture in computational commutative algebra. We continue our study about ideals, define prime and maximal ideals, and then we look at some operations on ideals. Definition. Let R be a ring and I an ideal. I is said to be a prime ideal if for all R and S inside R, R times S is inside I implies that R is inside I or S is inside I. So, for example, two Z is a prime ideal of I. A prime ideal of Z. In fact, if you take an arbitrary for all n, for all non-zero n in Z, nz is a prime ideal if and only if n is a prime number. One has to, for the statement to be true, one has to put non-zero n, because if you take n to be 0, then the 0 ideal is a prime ideal, but 0 is not a prime number. So the statement will not be correct as it is written. So here we only look at, so maybe one should just say that 0 is a prime ideal of Z. Definition. R, a ring, is an integral domain and often it is just, we'll just say a domain. We'll drop the word integral because it's very unlikely to cause confusion. If for all non-zero elements Rs is not zero. And then proposition, which is an exercise. R is a domain if and only if 0 is a prime ideal. We said last time that in one of the earlier lectures that 0 is always an ideal in any ring. Here, R is a domain if and only if 0 is a prime ideal. Now we look at another kind of ideals. An ideal I of R is maximal if it's a proper ideal and there does not exist an ideal J such that I is properly contained inside J, which is also a proper ideal. In other words, I is maximal among the proper ideals of R. So one can show the exercises to show the following. R is a field if and only if 0 is a maximal ideal. If R is a field, then it has only two ideals, 0 and the full ring. So then this is clearly maximal, and one has to show the other way around. That if 0 is a maximal ideal, then every non-zero element is invertible. And another exercise. Every maximal ideal is prime but the converse is not true. So give an example. Of a prime ideal that is not maximal. So give an example of a ring and a prime ideal in it. In fact, we have already seen it, but I will not tell you what it is. Okay. So here is an important property about rings. Oh, sorry, before we import property, another definition. Let I be inside R be an ideal. Then we can give, so we know that I is a subgroup of the group R mod I is a subgroup of R plus under the additive operation. So we can talk about the quotient group that also has an induced action. The group can be given ring structure, meaning given a multiplication on top of this. So to this, we have to say what is multiplication, what is additive identity, and then one has to check that these properties satisfies the definition of a ring, but please do that. Ring structure by setting. So elements of this set R mod I are cosets, which we write R plus I, and then some S plus I. So these are cosets, and we define the product. So this is the definition. Rs plus I for all R and S inside R. Okay. So then let's just observe that the additive identity is the 0 of this group. This is the 0 of the group, which is a coset of 0, and multiplicative identity is the coset of 1, and it is a so this is called the quotient of R by I, and it's again denoted by R mod I. So rarely there will be a confusion whether one is referring to the quotient group or the quotient ring, but we'll make it clear if it is. Okay. So this is what it is. So now let's look at an example on how this is done in Macaulay. So this is an example that we saw in the first lecture. We asked Macaulay Z mod 17 and it understands it correctly, and this is what it said, it's a quotient ring. Okay, so now let's look at one more example on finding the kernel. So this goes back to the example that we saw, the first example that we saw of a ring map, polynomial ring in 2 variables, mapping to a polynomial ring in 1 variable t, x goes to t square, y goes to t cube, and we ask for its kernel. Then we ask for the quotient ring R modulo the kernel, and then we define a map. Okay, so this will be part of the exercises, that if there is a map from R to S, ring map from R to S, then there is a ring map from the quotient ring R mod kernel to S. Okay, so the existence of this you will verify in the exercises, and then there is an induced map, and you should run these lines of code in Macaulay 2 and understand what the output says. Okay, so I will not show you the output. This is part of the exercises that you should do with Macaulay. Okay, so here is the important property which relates. Okay, there exists a bijective correspondence between 2 sets. Ideals of R containing I and the other set that we are considering is ideals of R mod I. Now, what is the correspondence? If you have an ideal J here which contains I, that goes to the residue of I, and what exactly do we mean? This we mean R plus I, R inside J. So we just look at the cosets of elements inside J. So it's just, okay. So what, okay. And from this side, if you take an ideal of R mod I, so maybe I should, I should have said something before this. Let me add a line here. What is that? The map from R to R mod I, R goes to, let's call this map pi, R goes to the residue class of R, sorry, this is a line that I wanted to add, is a ring map, is a surjective ring map, ring homomorphism. Okay, so one needs to observe that thing, and if you have an ideal K here, then send that to the inverse image of K. Okay. Okay. So there is a bijective correspondence, so there is some things to be checked, that if you have an ideal containing I, then if you take on this side, it is an ideal of R mod I, and if you have an ideal of R mod I, call it K, then its inverse image under the map is, so this is a surjective map, so we can just anyway talk about its inverse image. It's an ideal containing I, so there is a bijective correspondence like this. Sorry, we are not, the proposition is not done yet. Okay. Under this correspondence, prime ideals of R containing I. So if you consider this set, this is a subset of the other one. This corresponds to prime ideals of R mod I. Okay. Similarly, you can replace prime by maximal here. and here also maximal. Okay. So from what we have said earlier, this is a subset of that, this is a subset of this, and both of these are, subsets of this. So there is a bijective correspondence here which restricts to a bijective correspondence on these subsets. And what do we mean by bijective correspondence? So in this particular situation, we have defined a function from the left side to the right. Here we have defined a function from the right side to the left, and both these functions are identity maps. So if you start from a j here, go there and apply this map, you will get j. Start from a k here, go here, and then take its inverse image and then apply this operation, we'll just get k. So that's why these are bijective correspondence. And under this thing, there is this map. And proof, so whatever I just said is the proof that bijective correspondence. So now I will just sketch. Okay, so proof. Okay, so the first part is check that the two functions are inverses of each other. Okay, that's straightforward. Now the question is, if you have a prime ideal here, so I'll just prove the first thing. I'll just prove this. Okay. So let P containing I be a prime ideal. Okay. We want to show that P mod I is a prime ideal of R mod I. Okay. So one can check that as follows. So P mod I is a prime ideal of R mod I if and only if R mod I mod P mod I is a domain. But what is this? This is just R mod P is a domain. Okay. And that is exactly the condition that P is a prime ideal. Okay. So now what about the maximal ideals? Use the fact that R mod I is R mod some Q is maximal. I'm sorry, that's not what I want to say. Q is maximal if and only if R mod Q is a field. Use this and then apply the same argument as one did for prime ideals, and similar argument will give. Okay. Okay. So now let's look at a couple of examples in Macaulay. So this is a simple command. So here we take the ring R, Q, Q, X, Y. Then we take the ideal generated by the product X times Y. And then we ask, is it prime? So there's a command called is prime. This is a capital P. Is prime ideal this? And it says it's false. And that's, because X is not there in this ideal, Y is not there in this ideal, but the product X times Y is there. So it's not a prime ideal. But of course, when you use commands like this, one should be a little careful. So let's try a very similar example. So now we look at the same thing, similar thing. R is a polynomial ring in one variable over the integers. Then we ask, is prime ideal X, which it is because polynomial ring in one variable, modulo X would just be integer, which is a domain. So this is, we know that this is a prime ideal, but if you ask Macaulay that question, it says expected base field to be QQ, and actually a few more, I chopped the, when I took the screenshot, I chopped the lines, but this is an error. That's because the thing has not been programmed to handle even cases like this. So before we use these commands, one should verify the context in which it would correctly solve. Okay. So it's just a minor warning when one tries to use these things. Okay. So now we look at some operations on ideals. Okay. The first thing is called extension. Okay. So F is a ring map from R to S. Okay. I an ideal of R. Now we can just look at f of I. Is this an ideal? Okay. This is not an ideal in general. Okay. In fact, one does not have to go very far to find an example. 2Z is an ideal of Z. Okay. Take F to be the natural map from Z to Q, which is the inclusion map. Integers sitting as rational numbers with denominator 1, and f of 2z, 2z is the set of even integers, this is the set of even integers. This is not an ideal of rationals. And that's because the set of rationals is a field. There are only two ideals, 0 or the whole ring, and this is just, it's neither 0 nor the whole ring. So it's not very difficult to see this thing. Okay. But definition, the ideal generated by, ideal of S generated by f of I is called the extension of I to S. Okay. It's sometimes called the extended ideal or the extended ideal. And notation often is just IS. Quite often the map is clear from the context. In any case, this notation means the ideal generated by the image of I under F inside S. F was defined to be this map from R to S, x goes to t square, y goes to t cube. Yeah. So we ask f of x. It's at t square. Now we ask f of ideal generated by x square and y, and Macaulay has been programmed to realize that f just taking the set theoretic image is not going to give an ideal, so just take the ideal generated by it. So Macaulay already outputs the ideal generated by it, and x square goes to t to the 4 and y goes to t cube, and f of the ideal is the ideal generated by these. One more example. So this is the example in which we asked, okay, so let's unravel this thing. So the point of this example is that we don't need to label all these things all the time. So here we take the map from Z to QQ, and Macaulay knows what that map is. Okay, so that's between this bracket and this bracket. Apply to the ideal generated by 2. So this is going to be an ideal of Z. We're applying this map to Z, to this ideal. and then we ask, is it equal to, so the two, this equal to the set of rationals, the ring of field of rationals, and it says it is U, it is true, okay. And the first point that you already mentioned, it's not necessary to label all these things, one can just compute it like this. And the brackets here that I have used are to demarcate the expression here, so that Macaulay 2 understands what we wanted to understand. So you should do an exercise in which you remove various pairs of brackets here and see which ones work and which ones don't. One more definition. Contraction of ideals. Okay. So again, F from R to S ring map. Okay. This time J is an ideal of S. And we ask, so what can we check? F inverse of J is already an ideal of R. And F inverse of J, and called the contracted ideal. So now let's look at. So here we look at R, which is polynomial ring in one variable over the rationals, variable x, here y. J1 I define to be an ideal like this. So just note that if we don't, so the semicolons suppress the output, and we don't need to see, if you put this command, we know what it does. We don't need to see the output specifically, so we can put a semicolon, and if you put a semicolon, you can give multiple commands in the same line itself. So I just put 3 of them in one line, 2 of them in the next line. So this is just F. Okay. So J2 is ideal generated by y cube, and F is this map. Okay. So what does this say? This says x, under this map x goes to y square. Okay. Then we ask, so the command in Macaulay is pre-image of F comma J1. So this is just F inverse of J1, and here it's F inverse of J2. And here, so I'll just show you the relevant output. Pre-image F comma J1, this is F inverse of J1, is the ideal generated by X, and pre-image of the ideal generated by pre-image of J2 under F is the ideal generated by X squared ideal of R. So you should verify these calculations by hand. So now we continue a little bit more of these things. So next is radical. The radical of I an ideal, is the set. So which we denote by the radical symbol R in R, such that there exists some integer greater than or equal to 1 such that R to the m is inside I. The radical, okay, so the first point that we would like to make note is that I itself is in the radical of I, because you can just take, for elements of I, we can just take m to be 1. Okay, so I, sorry, that's the definition. Here we are liking some properties. Okay. Another property is that radical of I is an ideal. Okay. So this I will sketch the argument in the exercises. And few more properties that again you will work out in the exercises. So before that, we just say a definition. Say that I is a radical ideal if radical of I equals I. Okay. So some exercises. Prime ideals are radical. Exercise 1, 2. Let's say that we have a family of radical ideals, I lambda, lambda in some index at lambda. Then the intersection, so there could be an arbitrary family, is radical. A definition. The nil radical of R is the radical of the zero ideal. In other words, elements for whom some positive power is zero. And an exercise. Radical of I is the pre-image of the radical of the nil radical of R mod I. Okay. For the natural map, surjective map or rig map, surjective.